This video shows a direct proof example to show that the sum of integer cubes from 1 to n to the power 3 is equal to sum of integers from 1 to n then raised to the power 2, or basically squared. Okay, so what we are trying to show is sigma, first line, k from 1 to n, k to the power 3, or cube, is equal to sigma j from 1 to n on j, and then the whole thing raised to the power 2, second line. So, okay, how is this possible? There is a quick way. I'm going to use the trick that binomial expansion, when I have a plus 1 to the power 4, a being an integer, then I have a to the power 4 plus 4 times a to the power 3 plus 6 times a to the power 2 plus 4 times a to the power 1 plus 1. So this is binomial expansion for expansion by power 4. And these 4, 6, 4 are just coefficients of binomial expansion. So the trick I'm going to use is, let's write n plus 1 to the power 4. So in this case, it's easy. A is n, so I'm going to get n to the power 4. So I'm going to get n to the power 4 plus, then 4n to the power 3 plus 6n to the power 2 plus 4n plus 1. Great. Now let's do the trick. For n to the power 4, I'm going to write it this way. n minus 1 plus 1 to the power 4. So there is nothing wrong with that. Okay, but now my a is n minus 1. So it becomes n minus 1 to the power 4 plus 4n minus 1 to the power 3 plus 6n minus 1 to the power 2 plus 4n minus 1 and then plus 1. You can keep doing this. Let's do one more time, but that will be the last time I'm doing for these, and then I'm going to jump to the conclusion. So for the next one, effectively n minus 1 to the power 4 can be written as n minus 2. So I'm going to write it as n minus 2 plus 1 to the power 4. So it's the same story. You would get n minus 2 to the power 4 plus 4 times n minus 2 to the power 3 plus 6 times n minus 2 to the power 2 plus 4 times n minus 2 plus 1. Okay, so if you keep doing this, so ellipsis, if you keep doing this, then you would get finally to say, let's say 3 to the power 4, which I'm going to write it as 2 plus 1 to the power 4, which is 2 to the power 4 plus 4 times 2 to the power 3 plus 6 times 2 to the power 2 plus 4 times 2 to the power 1 plus 1. And lastly, 2 to the power 4 itself can be written as 1 plus 1 to the power 4, which basically just 1 plus 4 plus 6. And of course you have these things, right? 4 times 1 to the power 3, 6 times, and then you have 4, and then you have 1. So what's the benefit of doing this? Okay, the benefit is systematic summation. So what we have, if I start summing up all these things, so by that I mean, let me move this equal here, and maybe this whole thing a little bit this way. Okay, it's good enough. So I mean, if you start summing up the left-hand side of these equalities that I have written, so you add up these guys. So you add up, if you start adding up all these components, so add them. And of course, at the same time, you start adding up everything on the right-hand side of the equality as well. So everything on the right-hand side. Now, the beautiful thing is, as you can see, this n to the power 4 cancels out. Let me use a different color so that it's visible. So this n to the power 4 cancel out with this n to the power 4. This n minus 1 to the power 4 cancels out with this side, which is n minus 1. This n minus 2 to the power 4 cancels out. This 3 to the power 4 cancels out with the one here that is also 3 to the power 4 plus something. 2 to the power 4 cancel out with 2 to the power 4. So what remains, when I add up all these guys, I'm going to write it here. So what remains, let me go back to my color. Okay, so I get on the, okay, so on the left-hand side of this equality, I get only n to the power 4 n plus 1 to the power 4 standing. So n plus 1 to the power 4, n plus 1 to the power 4. On the other side, I have only 1 here, so 1 plus. So now I have 4 times, so maybe I use a different color again so that you can see it. I have 4 times all these guys added together. So don't forget that we have these ellipses. Okay, that's exactly the summation I want, because when you add 1 cube plus 2 cube up to n cube, that's exactly the summation, but there is times 4. So I get 4 times this summation that I'm looking for, the sum of integer cube. So keep that plus. Okay, so I'm going to go with, let's say, now you can see that the next one is 6 times the sum of integers squared. So I'm going to write it. So, and after that, you will see that 4 times the sum of integers. Okay, so I'm going to go back to the color I had. So I was writing 4 times s plus 6 times. Now we have the sum of sigma from k1 to n, but k squared. That's for these guys. And finally, I have 4, just the sum of integers, sigma. So the sum of integers from k1 to n, just k. And finally, I have just n times 1 that I add them together. So naturally, that become n. Okay, we're almost done. How? It's well known, and in a separate video, I have proven that the sum of integers squared, so from 1 to n, k squared, this is equal to this identity. So this is proven. I'm going to use it. So I'm going to use basically what I'm going to say, combination of equation 1 here and equation 2 here. I'm going to say from 1 and 2, this is discussed in a separate video, and then that you can find under the math channel. So you can see that here we can write n plus 1 to the power 4. So I'm going to keep this, and then equal to, so equal to 1 plus 4s that I want to, let's say, figure out. And then after that, what do I have? I have, okay, so what do I have? I have 6 times, from 2, I'm going to substitute for this portion. So I'm using 2 now. So 6 times this entity that you see here. So n cubed divided by 3 plus, so n cubed divided by 3 plus n squared divided by 2 plus n over 6. And for this one, sum of integers, it's well known that sum of integers is just simply n times n plus 1 divided by 2. So I get 4 times n times n plus 1 divided by 2, and finally I have plus n. Okay, almost done. So I need to keep this here, but I can move everything to the other side. So what I can say now is 4s, the summation that I'm interested in, sum of integer cube, is equal to, you can see that, let's just simplify. So n plus 1 to the power 4, and then minus 1 minus 2n cubed minus 3n squared minus n plus n, and then plus 2n squared, sorry, let me just make sure I'm not missing something. So minus n, and then we have minus 2n squared minus 2n, and then finally we have minus n. Okay, so what's the benefit? All right, so the benefit is we can simplify this, and if you do so, you will see that this will turn out to become equal to 4 times, will be equal to, let me just make sure. Okay, so it will be exactly equal to n to the power 4, n to the power 2 times n plus 1 to the power 2 divided by 1. So that will be exactly what is going to turn out. And then we won't need to divide by 4, so it becomes s is equal to n times n plus 1 divided by 4 to the power 2 to the power 2. And that's exactly what we wanted to get to, because we are now showing s is n times n plus 1 divided by 2 to the power 2. But this entity here is well known to be the sum of the integers. So as a result, we have s equal to 1 plus 2 plus 3 plus up to n to the power 2. That is exactly what I wanted to show, because s is the sum of integer cube, and this on the other side I already got that it's the sum of integers raised to the power 2. I hope that this direct proof example is useful and helpful.